So we're starting a new unit on this one. This is the rational number system. So our number system has evolved over time. On the following pages, we'll review some subsets of these numbers that are included in the sets of rational numbers, such as whole numbers. Alright, whole numbers are indicated also by the symbol W. But it's kind of like a fancy W like this. Some people connect it like that as well. So this would be whole number symbol. Whole numbers are numbers such as 0, 1.
So it's like a base number.
2.
There's no decimals.
3. Now it's important that we see all of these, alright? 4. 5.
You sound like one of those.
Now I'm doing pretty well here, alright? 6.
You sound like one of those like.
Oh, I remember.
Little kids shows.
7.
What? How many
If the
pennies are
pace of test
there?
for this.
1. How much debt do we
And this goes on forever.
Miles.
So whole numbers, yes, do not have decimals. As these do not, even though they do, we just don't show them, alright? But these would be whole numbers. There's one other before whole numbers. Alright, natural numbers are also indicated with the very fancy N.
Oh, I might write my name like that now.
So, natural numbers are numbers such as 1, 2, 3, 4, 5, 6, and it goes on forever. Now, there's a big difference between natural numbers and whole numbers. Alright, you guys can see the difference between these two
I remember this in 6th grade.
is that natural numbers do not have a 0. Whole numbers do. That is because 0 does not actually occur in nature, which is why it's not natural.
Then what about extinct?
Whole numbers, 0 is a whole number. It's a whole lot of nothing, which is why it's included in the whole numbers. But again, it's not really a natural number. We know this especially because 0 eluded mankind for many, many years, for many millennia actually. It was not the Greeks or the Europeans who discovered 0, it were the Aztecs who quantified the value of 0.
We already have history
The
class.
value of 0 is.
Alright, integers. Integers, just like whole numbers and natural numbers, are indicated with a very fancy I. Bam.
What's a Z?
That is not a Z. That is an extremely fancy I. Well, it's a capital I. It's not a lowercase I.
That is not an I, that is a Z.
I think you guys might need glasses again.
already have one.
May need thicker ones. Alright, integers are numbers such as 0, 1, 2, 4, 3, and so forth.
Wait. So what's the difference between integers and whole numbers?
Integer.
Well, integers and whole numbers are extremely different because integers not only include all of the whole numbers, but also their negatives.
I knew that.
Now notice on this list, we have 3 dots going to the left and to the right, meaning it goes all the way to, well, as far as you want to take it on that stuff.
Then he'll say.
But it's also important to notice that there are no decimals shown yet. Rational numbers are numbers that can be described in a few different ways. But not only can they be written as proper or improper fractions. So rational numbers can also be terminating or repeating decimals. Let's look at some examples of all of these. So let's first look at proper and improper fractions. A proper fraction would be something like 1/2, maybe 1/4,
3/8.
2/3, 3/8, something like that. Improper fractions is just where the numerator is bigger than the denominator, like 8/5, 10/1, something like this.
Should we keep putting this on the number line?
That is correct. Any whole number integer or natural number can be written like we have here with 10 over 1. So that makes them rational numbers as well. So let's look at terminating decimals now. Terminating decimal would be something like 0.5.
That's 1/2.
Terminating decimals are actually repeating decimals though. Let's look at some repeating decimals, then we'll come back to that. So a repeating decimal, one that we're extremely used to, would be something like 0.3 repeating. Or maybe something like 0.1 repeating.
Wait, what's 0.1 repeating?
Sometimes the decimal has many numbers that repeat, like 5, 1, 2, and then all three repeat.
3.
So 1/3 would be.
Alright, now that first number, the whole value in the ones place does not have to be a 0. Sometimes it can even be negative, so like a negative 7.883. And maybe only the 3 repeats. Maybe it's just the 8 and the 3 right there that repeat. It doesn't matter. That would be called a repeating decimal, which we use bar notation to indicate. Now, terminating decimals are just a very special form of repeating decimals. What number is repeating in terminating decimals? 0. So you could have something like 1.5, and then the 0 repeats. But again, we just don't show it, which is why we terminate it.
Terminator.
But it will be back.
That soundtrack.
Hasta la vista, baby.
Amazing.
All right. You could have something like a 0.125. Maybe a 10.125. Negative. Doesn't matter. All three of these still terminate at some point. All right, so we got 1, 2, 3, 4 types of number sets, and as it turns out, all 4 of these are considered to be real numbers. Now, we do have to call these real numbers because there are such things as not real numbers, but we're not concerned with that in this class. Now, some of you guys noticed as well, for example, starting with natural numbers, which is the most basic type, we have 1, which also appears in whole numbers, integers, and it can show as a rational number because we could write it as a fraction. So what that means is that some of the numbers are classified many times, and we will have to do that later. Over the years, you have expanded your knowledge of the number system gradually, incorporating the sets of numbers mentioned above. These sets of numbers are all part of the rational number system. A rational number is any number that can be expressed as a fraction, where the q, the denominator, is not 0. That's correct. Okay, so begin to fill out the table below with different subsets, including equivalent forms of rational numbers you know about so far, and give a few examples of each. You'll continue to add to this list throughout the section. That's actually what we just did right up there at the top. Yeah, let's look at that. Natural numbers are a subset of whole numbers because they're all included in whole numbers, but whole numbers also includes 0. Whole numbers are a subset of integers. Integers are a subset of rational numbers. Now, it doesn't mean that there always has to be more, but sometimes there is. So we did show some examples of those and describe them as well. So we have to be able to change numbers into, well, fractions specifically into decimals.
I've done the.
Change the following rational numbers into decimals without the use of a calculator. We need to be able to do this anytime by using long division. This one's an easy one, you guys know it, but let's just look at it because long division is easy as well.
I know that one.
Because this one would be 1 divided by 2.
It's 0.5.
My table.
Alright, I already said I was going to use long division, so please be patient. 1 divided by 2 would look like this. And we see that 2 does not go into 1, so we're going to make that a 10 with the decimal. And I line up the decimals because no one remembers how to do long division anymore.
I do. I know.
Well, 2 goes into
I do.
10 5 times, and 2 times 5 is 10. When I subtract, I have 0 remaining. And then I can say to myself, how many times does 2 go into 0? It doesn't. So I can drop another 0 and see if that helps.
No.
Well, how many times does 2 go into 2 zeros?
0.
0. Well, that means I need another 0 to drop down. How many times does 2 go into 3 zeros?
0.
0 times. Now that means that the zeros repeat, but we don't like to see that it repeats because we're lazy math people. So we just get rid of that garbage and say that it terminates, giving us our final answer of 0.5. Let's do some more long division.
I just like giving people chocolate.
This is 9 divided by 5. All right, 9 divided by 5. So long division, this is 9 divided by 5. And 5 actually will go into 9 once. So 1 times 5 is 5. Subtract that out from the 9er. And we had 4 remaining, but since we're using decimals on this, we're going to make that 90 and drop that down to make that a 40. 5 will go into 40 8 times. 8 times 5 is 40. So it went to 40, exactly 40. 8 times 5 is 40 exactly. And we have a remainder of 0. And again, we could keep dropping zeros and see that the 0 repeats. But there's no need for that.
Wait, so I need to explain.
But that would be a terminating decimal right there. Alright, so once again, just may help to see this as division, because some people are still not acknowledging that the fraction line is division. So I've got 1 divided by 7. This one's going to be a little bit bigger, so I got 1 divided by 7.
Oh.
So
Backwards.
I got 7. How many times is 7 going to 1? 0.
7.
So I'm going to need a 10 on this thing. 7 will go into 10 once. So I do 1 times 7, which is 7, and subtract that, and I've got a 3. Well, then I need a 0. How many times is 7 going to 30? 4. 4 times 7 is 28. I'll subtract that, and I got 2. But that means that 7 won't go into 2, so I need to drop another 0. Very good. 7 will go into 20 twice. 2 times 7 is 14.
Drop 0.
7 will not go into 6, so we're going to have to make that a 60.
Oh my goodness.
And now you put an 8.
7 will go into 60 8 times. Very good. 8 times 7 is 56. Thank you. So we're going to subtract 56 right here, and we got 4. So we're going to have to drop another 0. 7 will go into 40. 7 times 5 is 35, and I subtract, and I got a 5. And I do need to drop another 0.
I'm going to it 7 times.
Alright, so 7 will go into 50 7 times. 7 times 7 is 49er. And we got 1. Well, the 1 is the number we started with. We can look at that and drop another 0, by the way. 7 will go into 10 once. But now that we have that, it's just going to start repeating through this whole entire process that we have right here. So that means once we have a number that comes back, it's going to repeat, but it's all the numbers that go back to the number that repeated. So it's the 1, 4, 2, 8, 5, 1, 7 with bar notation. We don't need the 1 anymore.
You're just going to erase it.
All right, and that would be the bar notation for this problem right here. So this is 3/8. We're going to change this to a decimal. And to do that, I'm going to do 3 divided by 8. But I am also going to use long division. So I have 3 divided by 8. And 8 does not go into 3. So I'm going to make that 30 and keep the decimal in the same place value for my answer. 8 will go into 30 3 times. 3 times 8 is 24. And when I subtract, I got a 6. 8 won't go into 6. That's good. But I need to drop a 0 so that it can go into something. 8 goes into 60 7 times. 7 times 8 is 56. Subtraction. And we got a 4, so we're going to need another 0 to drop. And 8 will go into 40 exactly 5 times. 5 times 8 is 40. Subtract, and we have 0 remaining. And this would be our decimal value for 3/8 or 3 divided by 8. On this one, alright, on this one also, this is 1 divided by 3. So using long division, I've got 1 divided by 3. Now this is extremely difficult because 3 doesn't go into 1, but we're going to make that a 10. That's not what that 0 right there. And a 3 will go into 10, exactly 3 times. 3 times 3 is 9. I subtract and I got a 1. Well, then I'm going to need another 0, and I got this 10. But the nice thing about this is we can see that we're starting with this number that immediately gave us the same number down right here. That means the 3 is going to repeat, and I'm done with bar notation. Now let's look at this. I mean, some of you guys may not have noticed that right away, which is alright. 3 goes into 10 exactly 3 times, right? 3 times 3 is 9. And then hopefully we can see the pattern right away. We got another 1. But again, we don't really need to show that 3 because it is repeating. 4 divided by 15. So let's show this one using some long division. 4 divided by 15. 15 won't go into 4. So we'll make that 40. 15 will go into 40 twice, which would give us 30, subtraction. I got 10, so I'm going to need to drop another 0. Looks like it's going to go into it 6 times. And 6 times 15 should give us 90. So when I subtract, I get a 10 again. So notice, I had 10 right here, and I've got another 10.
It's repeated.
Which means it's going to repeat, but we have to be careful on this. It's not the 2 that's going to repeat.
It's just a 6.
It's just the 6, and let's show that that is what would happen. If I drop this 0, then I got 100. And how many times is 15 going to 100? We've seen that already. It's going to go into it 6 times, which is going to give us 90. Subtract, and we got another 10. So it's just the 6 that repeats. If you show it like this on the test, that's okay. We don't need to see that only 1 6 is repeating. This will do. Yeah, do not show that 6 in the red right there, because we can't show that you can't have a number after repeating numbers. What do you notice about the decimal expansion of any rational number? Why is this true? The decimal will always repeat, even if it's a 0 that repeats, and that's only for rational numbers like the fractions we were just looking at. Why is this true? Because any number, any decimal value that repeats can be placed into a fraction. Alright, so are all numbers rational numbers? No.
Just like pi.
Are there any numbers that cannot be written as a quotient of 2 integers? Yes. Yes, there is. What about square root of 2? Can you write square root of 2 as a fraction? Sure. Square root of 2 over 1.
Doesn't pi?
But is this rational? It is not rational though, because this would give you some decimal value.
1.14.
Something like 1.414, but then it has more values after that.
But doesn't?
So this one is considered still irrational. So yeah, we can't say that all numbers are rational because not all numbers have a decimal that will repeat or terminate. Like the square root of 2, the reason why this is still considered irrational is because it has a square root in the fraction. Which in a way kind of makes it, well, it's not proper or improper, it's just irrational. There's no way we can write these as whole numbers, and the square root of 2 is not a whole number. Numbers like the square root of 2, which do not have a terminating or repeating decimal expansion, are irrational numbers. Irrational numbers cannot be expressed as a fraction or quotient. The symbol for irrational is quite complex. It is IRR. Bam. Alright, rational and irrational numbers together form the set of real numbers. Real numbers can be thought of as points on an infinitely long line called the number line, which we have seen before. But what they really want us to do is to draw a Venn diagram. So if these are considered, if this box contains, what the heck? Alright, real numbers. Now, subsets of real numbers would be what we call rational numbers.
Wait, are we drawing this?
But if we do split this up, the real numbers, the other part would be irrational numbers. Alright, now the irrational numbers, there's quite a few of them. In fact, there's just as many as the rational numbers, I suppose. But we got those rational numbers, which would be this box right here.
Why don't they have a...
Alright, so this box right here in red would be the rational numbers, but as part of the rational numbers, or a subset of the rational numbers, we go into integers. Bam. And then inside the integers would be these ones right here. Alright, inside the integers would be all of the whole numbers. And then inside of the whole numbers would be the natural numbers. This is what we call a Venn diagram. Alright, and then as a whole different set of numbers, we have non-real numbers. So this is non-real numbers, again, which is separated completely from all of the real numbers, because they're not real. You either have a real number or a not real number. Classify the following numbers and provide a justification. So it is a big chart, but all we got to do is put check marks in whatever classifications these are. 2/3, for example, is not a whole number, integer. It is a rational number there. Is it irrational? No, because it's rational. Is it real? Yes, it does exist. The justification is because it's rational. Well, I guess it's a proper fraction. Alright, 0.25, this one is a terminating decimal, so it's rational and real.
Wait, have you ever...
Alright, -2. -2 is real.
Yes, wait.
It is rational, and it's an integer.
Yes, I got.
Alright, the square root of 5, if we put this into a calculator, it would give us a really horrible decimal. It is real, and it is also irrational. The square root of any non-perfect square is automatically irrational. Automatic.
Aren't all of these
10, this one is whole. It's an integer. It's rational. It's not irrational. It's real. Bam. Now, they didn't put natural numbers on this, which is okay. 0 is a whole number. It's an integer. It's rational. And it's real. Alright, you guys take a moment and do 7 through 11.
Is 10 a...
And then we'll look at the answers on these. Alright, now it's important for you guys to realize if it's checked off on the left, it's automatically everything on the right except for unless it's irrational. There are the answers for these. Alright, let's go through some of these. So 10/13, that is a proper fraction, which means it's a rational number, which means it also must be real. 13, that is a pi. Pi is irrational, but it is also real. So -3 pi's would still be an irrational number that is real. 0.26, only the 5, 4 repeat. That one is rational, which means it is real.
How would you...
Alright, 16, the cube root of 27 is actually 3. 3 is a whole number, which is an integer, which is rational and real. Alright, so yeah, on this one, we see the pattern right here, is that you got a 2, then you got a 1 with 2 2's, 1 with 3 2's, 1 with 4 2's. So the next one would be 1 and 5 2's. While we can predict the pattern, that doesn't mean that it's rational. This one would still be irrational, because it never repeats or terminates. So it's irrational, and it's real. All right, the cube root of 30, that's not a perfect cube, so that's going to be irrational and real. The square root of 2, whether we divide it by a whole number or a rational number is not going to make a difference. It's still going to be irrational and real. The side length of a square with an area of 2, so its side length would be the square root of 2. That's irrational and real. The side length of a square with an area of 9, that would give us a length of 3, so that now is whole, integer, rational, and real. The number halfway between 3 and 4, which would be 3.5, that is rational and real. The number that represents a loss of 5, that would be negative 5, so that is an integer, which is rational and real. All right, that is the chart right there.